All right, let's dive into the world of fluid mechanics, the science of basically everything that flows. It's this incredibly complex, beautiful field. But here's the crazy part. To even begin to understand it, scientists have to start by telling, well, a few very useful lies.
And yeah, you heard that right. That's a direct quote, and it just perfectly sets the stage for what we're going to talk about. Now, this isn't about, being deceitful. It's about something much, much cooler. It's a scientific tool that lets us tackle problems that would otherwise be completely impossible to solve.
So, what exactly is this big foundational lie? Well, in the world of applied math, they have a fancier word for it: approximation. And the first, the biggest, the most important one in all of fluid mechanics is something called the continuum hypothesis.
Okay, so think about it. We all know that any fluid, water, air, you name it, is made of just gazillions of tiny molecules, right? All zipping around like a chaotic mess. Trying to track every single one of those? Forget it. It's just impossible with today's computers. So the continuum hypothesis does something totally brilliant. It just says, you know what? Let's just pretend those molecules aren't there. Yeah, let's treat the fluid like it's a perfectly smooth, continuous blob of stuff. By doing that, we can suddenly talk about things like density or velocity at any specific point in the fluid. It's an incredibly powerful trick, as long as you remember not to zoom in too close.
And that right there, that's the whole game. The art of fluid mechanics isn't about getting every single tiny detail right. It's about knowing what you can safely ignore. The physics is just, it's too complicated to solve head-on. So the real genius is in the approximation. And what's the very first thing we toss out? The atoms themselves. Wild, right?
Okay, so we've agreed to our first big lie. Our fluid is a smooth, continuous thing. Awesome. But now, how do we actually watch it? How do we describe its motion? Turns out, there are two totally different ways to look at it. First up, you've got what's called the Eulerian way. This one's easy. Imagine you're standing on a bridge, just watching the river flow underneath. You're fixed in one spot, and you're just measuring the speed of the water as it zips past you. Simple enough. But then there's the other way, the Lagrangian description. For this one, imagine you toss a little rubber ducky into that same river, and then you run along the bank following its exact path. You're not fixed anymore. You're moving with the piece of the fluid, tracking its entire adventure. See the difference? Two totally different ways of seeing the same flow, and each one is useful for different kinds of problems.
So naturally, these two different ways of seeing the flow give us two different ways of drawing it, of visualizing what's going on. And that brings us to two really important ideas: path lines and streamlines.
Let's start with a path line. A path line is basically the rubber duck view. It's the complete historical record of where one single particle has been. Imagine our little ducky had a pen attached to it, just drawing its route on a map as it floated along. That line, that's its path line.
And this visual here shows it perfectly. That single curve, that's a path line. It's literally the history of one particle's trip through the fluid. Think of it like taking a long exposure photo of a single firefly at night. You don't see the firefly, you just see the beautiful streak of light it left behind.
Now, a streamline, that's a completely different beast. A streamline isn't a history, it's a snapshot. Imagine you have a superpower and you can just freeze the entire river for one single instant. And at that exact moment, at every single point in the water, you draw a little arrow showing which way the water wants to go. If you connect all those little arrows, you get these beautiful flowing curves. Those are streamlines. They show you the direction of the whole flow, everywhere, but just for that one frozen moment.
And check this out. Here you can really see what I mean. These are two different snapshots of the same flow's streamlines, just taken at different moments in time. See how they're not the same? That tells us the flow is unsteady. It's changing and evolving. And this is the absolute key takeaway. When the flow is unsteady, the instantaneous picture from a streamline will not be the same as the historical journey of a path line. They're telling you two different stories about the fluid.
Okay, let's take a breath. So far, we've pretended atoms don't exist, and we've picked how we're going to look at our fluid. We're building this awesome, simplified model of reality. So, what's next? What other useful lies can we tell to make our lives even easier?
All right, here's another whopper. We can just pretend that fluids are incompressible. What does that mean? It means we're going to assume you can't squeeze them. At all. Like, you can't pack the molecules any closer together no matter how hard you try.
Now, this little lie comes with a really fascinating trade-off. On the one hand, if you assume a fluid is incompressible, it means its density never changes, it's always constant. And believe me, that makes the math so much simpler to solve. But there's always a but, right? There's a price. And the price we pay is that we have to completely ignore the existence of sound. Because what are sound waves? They're literally waves of compression and expansion moving through a fluid. So by making this assumption, we're basically saying, okay, we're only going to look at flows that are happening much, much slower than the speed of sound, where those compression effects are so small we can just pretend they're not there.
Okay, let's bring it all home. We've gone from ignoring atoms all the way to ignoring compressibility. And what we've seen is that fluid mechanics isn't really about finding some perfect single equation for everything. It's really an art, the art of smart approximation. So let's just quickly recap the big lies we've told ourselves today. First, the continuum hypothesis. We pretended atoms don't exist so we could have a nice, smooth fluid. Then we chose our viewpoint. Are we standing still or are we floating along with it? That gave us streamlines versus path lines. And finally, we pretended our fluid can't be squeezed, which simplified the math but meant we had to ignore sound. Every single one of these is a deliberate choice, a useful lie that lets us build a model of the world that we can actually solve and understand.
But here's the thing. This whole idea, this art of approximation, it's not just for fluid mechanics. It's kind of how all of science works. Heck, it's how we work. It's at the very heart of how we make sense of an incredibly complex world. And that kind of leaves us with one last question to chew on. What are the useful simplifications, the beautiful lies that you use every single day to navigate your own life?